Today, we will be talking about our new lesson, which is about pointers and dynamic arrays. Before everything else, let's first talk about the basics of what a pointer is. For this chapter, we'll be talking about the basics of pointers, dynamic arrays, and classes and dynamic arrays. To start with, let's first talk about what a pointer is. In C++, when we say pointers, they are usually the memory address of a variable. Actually, that's how we define a pointer in C++. They simply point to the memory address in which a variable is stored. Memory addresses can be used as names for variables. As opposed with regular variables, we usually use names to refer to them as storage for data used by our program. However, in the case of pointers, pointers actually contains memory addresses which refer to the location of our variables. If a variable is stored in three memory locations, the address of the first can be used as a name for the variable. When a variable is used as a call by reference argument, its address is passed, as opposed to how we usually use arguments, which are passed by value. Of course, pointers tell where to find a variable. An address used to tell where a variable is stored in memory is a pointer, as we have defined earlier. Pointers point to a variable by telling where the variable is located. But how do we use pointers? To use pointers with our variables, we first need to declare our pointers. So how do we declare pointers? Pointer variables must be declared to have a pointer type. Here's an example. Let's say we would like to declare a pointer variable p that can point to a variable of type double. As you can see here, whatever type we have in C++ can also be declared as a pointer variable. As you can see here, we have a double data type. Hence, we would like to declare the variable p as a pointer with the type double. Hence, this will later on be used to contain the memory address of the variable that is being stored in this. As you can see here, the asterisk identifies p as a pointer variable, which means whenever you declare a variable and an asterisk is placed beside your variable name, that will tell C++ that we are indeed declaring a pointer variable. We can also have multiple pointer declarations, just like the way we declare multiple variables on a single line with the same data type. To declare multiple pointers in a statement, we use the asterisk before each pointer variable. Here's an example. In this line, we are declaring p1 and p2 as pointer variables which point to variables of type integer. On the other hand, v1 and v2 are variables of type int. Talking about the address of operator, as you can see here, the ampersand operator can be used to determine the address of a variable which can be assigned to a pointer variable. For instance, we have the following statement. In this case, we are assigning to p1 the address of the pointer variable v1. So this is how we do it. As you can see here, as a result of this statement, p1 is now a pointer to v1. v1 can be called as such or the variable pointed to by p1. So that is made possible by using the ampersand operator. How about the dereferencing operator? C++ uses the asterisk operator in another way with pointers. For instance, the phrase "the variable pointed to by p" is translated into C++ as this statement, asterisk p. Hence, the variable pointed to by pointer p. In this example, the asterisk is the dereferencing operator. Here's another example. As we can see here, v1 and asterisk p1 now refer to the same variable. As you can see here, we declared the following variables with the following initial value. In this case, the pointer variable p1 is being assigned with the address being pointed to by the pointer variable v1. Hence, p1 and v1 are now pointing to the same variable. In this case, a new value has been assigned to the pointer p1. So, if we are going to trace its output, we will be given the following. Why is that so? It's because p1 is currently pointing to the same location pointed by v1. Hence, whatever value that was assigned to p1 will also be reflected to the memory address being pointed to by v1, which is the same. Now let's talk about pointer assignment. The assignment operator is used to assign the value of one pointer to another, as what we have seen from the previous slide. Here's an example. For instance, if p1 still points to v1, then we have the following. Therefore, whatever change that was reflected on the other pointer variable shall also be reflected on the other one. Hence, this causes the following to name the same variable. However, we should also be careful with using pointers. Thus, we need to take care when making assignments to pointer variables. For instance, the following statement changes the location that p1 points to, which will be replaced with whatever location p3 is pointing to. And this statement will also change the value at the location that p1 points to. This is what happens. For instance, we have the following assignment statement. p1 is equal to p2. For example, before the said statement, we have the following. In this case, p1 is pointing to an address which contains the value 84, in the case of p2, pointing to an address containing the value 99. After executing this statement, this will now have the following scenario. As you can see here, p1 will now be assigned with whatever address p2 is pointing at, such as this one. Thus, they will now contain the same value. Here's another example. In this case, we have two pointer variables which made use of the referencing operator. In this case, they are currently pointing to these respective values. After executing this, whatever value is contained by the address pointed to by P2, that will also be reflected to whatever content is stored in pointer variable P1. So that's how assignment operators are used when working with pointer variables. Let's talk about the new operator and how it is used with pointer variables. Using pointers, variables can be manipulated even if there is no identifier for them. Here's an example. In this case, we will create a pointer to a new variable of type int. In this case, this variable has no name, or it can be called as nameless. Here's an example of that. In this case, we use the new operator to create a new pointer variable. The new variable is now referred to as asterisk P1 or the pointer variable P1. In this case, P1 can be used any place an integer variable can be used. Here's an example. As you can see here, you can use the said pointer variable in any way as long as it follows the same syntax. We also have what we call dynamic variables. Variables created using the new operator are referred to as dynamic variables. Dynamic variables are created and destroyed while the program is running. Here are some examples of pointers and dynamic variables. Here's a program which makes use of pointers and dynamic variables. Let's take a look at an example. We have the following program. In this case, we would like to demonstrate how we use pointers and dynamic variables. As you can see here, we declared two pointer variables of type integer. And in this case, we used the new operator to create a dynamic variable. Then after that, we assigned it with the value 42. Then we used the assignment operator to assign the address contained by P1 to this pointer variable P2, and we will now try to output their contents. Then after which, we assign the value 53 to pointer variable P2. Then we will also try to see their contents at this point. Then we declared another new variable, another new dynamic variable, although this time we are still using the same pointer, and this time we assigned it with the value 88, and we will again see their content at this point. So let's try to run this example. Here we go. So this is the output produced by our program. As you can see here, P1 and P2 have the same values as reflected here in our code, which is self-explanatory. Also the same here. We assigned P2 with the value 53 which understandably will also be reflected to P1, hence giving us the output of 53 and 53. Now at this point, we declared another dynamic variable. If we will remember a while ago, a dynamic variable is created and destroyed after it was used. And in this case, we have a new instance of an integer dynamic variable. And we assigned our pointer variable with the value 88. Hence, when we run our program again, they now have their own respective value. As you can see here, the new dynamic variable that we declared here will no longer affect P2 since it is now a new instance of a dynamic variable and is no longer pointing at the address pointed to by P2. Let's proceed. Talking more about dynamic variables are quite a unique kind of variables as we have seen in our example a while ago. Here's an illustration of what happened. As we can see here, we declared two pointer variables, and in this case, their contents are still unknown. Next, using the new operator, we declared an integer dynamic variable whose address is now being pointed to by P1, although the content is still unknown since it hasn't been initialized. And that is what we did here. At this point, we assigned a value of 42 to P1. Thus, the address pointed to by P1 contains the value 42. In this part, we assigned P2 with P1, which means whatever value is contained in the address pointed to by P1 will also be reflected with P2. Let's proceed at this point. At this point, we now assign the value 53 to the pointer variable P2. But we must remember that P2 and P1 is currently pointing at the same memory address. Therefore, both of them will both reflect the value 53. Next, at this point, we declared a new dynamic variable, therefore resetting the content of P1 to a new memory address. Hence, we have this. At this point, P1 is now pointing to a memory address whose content is still unknown. After which, we assigned a new value to P1. Thus, P1 is now pointing to a memory address which contains 88, while on the other hand, P2 retained whatever value and memory address it is pointing at. Talking about the use of new with class types. Using operator new with class types calls a constructor as well as allocating memory. For example, we have the following. Let's say my type is of type class. Then we can declare it this way. In this case, we create a pointer to a variable of class type myType. Then we call the default constructor. If we will remember in our previous lesson, we've already been introduced what a constructor is. Of course, it is a function which is called to initialize the instance of our object. And here are some examples of those. In terms of variables, of course, we've already been mentioned that variables makes use of memory. And of course, whenever we make use of memory, it only makes sense that we must also have some sort of basic memory management. Of course, every programming language requires such practice. Thus, in terms of memory management, we have an area of memory called the free store, which is reserved for dynamic variables. As we have seen a while ago, dynamic variables often contains memory addresses whose values are not yet known. Therefore, they need to be stored and given a reserved memory space. Thus, they are placed in the free store. New dynamic variables use memory in the free store. If all of the free store is used, calls to new will fail. But of course, that was a concern a long ago during the early days of programming. Around that time, programmers are really particular when it comes to choosing the right data type, as well as how they use those variables and get rid of them after use to free memory space, for the reason that during that time, compute resources are somewhat very limited. But of course, in today's modern computing, that is no longer a very big problem for us, since we now have computers with gigabytes of memories. But that does not mean that we can no longer use this practice in programming. Of course, it still makes sense that we still do memory management as far as our variables are concerned. That is still considered a good programming practice. By using memory management, that also allows us to recycle unneeded memory. In that case, we can release memory spaces that are no longer needed. When variables are no longer needed, they can be deleted and the memory they used is returned to the free store and therefore can be reused again. We also have the delete operator. When dynamic variables are no longer needed, we delete them to return memory to the free store. Hence, the reserved memory space are freed and therefore can be used again. Here's an example. In this case, we use the delete operator to free up the memory space previously occupied by the variable p. How about dangling pointers? Using delete on a pointer variable destroys the dynamic variable pointed to. If another pointer variable was pointing to the dynamic variable, that variable is also undefined. Thus, undefined pointer variables are called dangling pointers. This happens when a pointer variable has been deleted and there is still another pointer variable that is pointing to the memory location that it is currently pointing at. We also have what we call automatic variables. Variables declared in a function are created by C++ and destroyed when the function ends. So that is done automatically whenever we make use of local variables in our function. Their existence is only within our function. These are called automatic variables because their creation and destruction is controlled automatically. In this case, the programmer manually controls creation and destruction of pointer variables with operators new and delete. How about global variables? As opposed with local variables in functions, variables declared outside any function definition are called global variables. Global variables are available to all parts of a program. Global variables are not generally used. If they need to be used, of course, we must use them with precaution. We also have the concept of type definitions. What is this? A name can be assigned to a type definition, then used to declare variables. This is especially useful when we are dealing with pointer variables, which sometimes can get confusing. To do this, we use the keyword typedef to define new type names. Here's the syntax to do that. Of course, we use the typedef keyword followed by our type definition and of course our very own type name. Here's an example. As mentioned earlier, type definitions can be useful when we are dealing with pointer variables. Here's an example. This would help us avoid mistakes when using pointers. Thus, we can use type definitions such as this one. Following the syntax, we have the typedef keyword and of course, a known type definition, which is in this case, integer, and of course, our new type name. In this case, we would like to declare a type definition which refers to a pointer variable of type integer. Thus, from now on, whenever we would like to declare an integer pointer variable, instead of writing int asterisk, we will simply use the following type. Here's an example. Thus, doing so would be equivalent to this one. And here's another example of multiple declarations. As you can see here, declaring pointers can sometimes be confusing. Thus, by using type definitions, we can get rid of those simple errors which can bring serious effects to our program. Now let's talk about pointer reference parameters. Another advantage in using typedef to define a pointer type can be seen in parameter lists. Here's an example. As you can see here, we simply use typedef to declare our parameters. In this case, the first example is much easier to understand and less prone to mistakes as compared with this one, which at some point can be confusing. In this section, we were able to learn how to declare a pointer variable. We also learned how to assign a value to a pointer variable. We now know how to use the new operator to create a new variable in the free store. And we're also able to write a definition for type definitions using the typedef, which in this case, we simply made use of typedef to create a new type of pointer variables and simply use the new type name whenever we need to declare variables of pointer type.